All right, we're going to talk about section 4.4. And this deals with uniform circular motion. All right, those words describe everything that we're talking about. Uniform here means constant speed. Circular in a circle. And motion is just moving, right? So moving at constant speed in a circle. So let's sketch. If we have a circle, we have a constant radius. So if we consider a point on the surface of the circle, described by some position vector, r1, and then we look at a point at some later time described by r2, then we can say that the magnitude of those is equal. All right, if we're moving around in a circle with a constant speed, what do the velocity vectors look like when our object moving in a circle is at each of those points? Well, our velocity vector, let me use a different color. Our velocity vector is tangential to the surface, and that means that it's also perpendicular to the radius, right? Is that clear why that's true? I think that's fairly clear for a radius on a circle that a tangent line is perpendicular. So because each of those are perpendicular, we can now, draw our vectors in this way. So let's look at R1 and R2, and we're going to talk about delta R. And then we're going to do the same thing for our velocities. V1, V2, and delta V. Because the velocities are perpendicular to the position vectors in the same way, then I claim that these angles are the same. And while these triangles are not congruent because the velocity vector isn't necessarily the same length as the position vector, they're not even the same unit, it doesn't even make sense to talk about it that way, they are similar. Right, these are both isosceles triangles with the same angle, so they have to be similar triangles. What does that let us do? Well, similar means that the ratio of associated sides has to be the same. So what that means is I can say that delta R over, I'm just going to call R, equal to the magnitude of R1 and the magnitude of R2. And I'm going to do the same thing with my velocity vectors, delta V over magnitude V. That ratio has to be equal because they're similar triangles. Now, my goal here is to describe the magnitude of the acceleration. So, goal here is acceleration. In order to get to that, well, we know that the average acceleration is delta V over T. So I'm going to solve for delta V here. In this way. And I'm doing it with deltas, but you can think of it as taking the derivative of both sides, right? Here, I'm just going to divide by delta T on both sides. It's the same process. And I'm just going to group my deltas on this side. All right, so now moving along, I did this because I'm looking for acceleration. So I'm going to consider this together, but we can also recognize that delta R over T has meaning as well, right? The change in position over a change in time is a velocity. So what we're left with is that A is V over R times V, so V squared. And this is the magnitude of the centripetal acceleration. All right, this word centripetal means center pointing. Well, we haven't really talked about why that's true yet, but we can go back up and, or just sketch it out again and look at our drawing. So consider again our drawing, R1, R2, and then we've got V here and V here. Well, let's do what we do and shift our vector over. I shift my V2 over here, and I talk about my delta V between those vectors. It's center pointing. If you consider that they have the same length, and if we take that differential value and let it get as small as possible, so these two positions are approaching an instantaneous value, you see that the acceleration is inward pointing. And that's the last part. We just talked about the magnitude, so now we have the direction. The acceleration for uniform circular motion is given by V squared over R toward the center. So an important thing to note here, the acceleration is not constant because it's constantly changing direction, but it is constant magnitude for uniform circular motion. And we'll do some practice problems with this, especially once we start doing forces. We'll do a bit more of these.